Oh, the one is here.
Yeah. I don't know.
Yeah, pretty early.
Look at here.
I thought Dr. Yu would be here.
Yeah.
Oh, the time is. Maybe
Oh,
we
no.
can correct the time, right?
That's off. It's at 3:53.
Let's correct the time.
Why don't we correct it?
Yeah, no. Let's finally correct it. Yeah.
What's the time?
3:53. I bet that's been incorrect for like 4 years. Oh, more and more.
3:53, right?
Yeah. Go by another hour.
Why?
Oh, because it's not. Because that's at 2:50.
Oh, okay.
Three.
My bad. Okay, so
Yeah.
53. That's it, right?
Yeah. About.
Why didn't anyone?
I don't know. People just get used to it.
How am I supposed to?
Who?
Oh,
Oh,
I can do it. Let's see.
sure. It's difficult. You have to fit that in there.
Okay.
Oh, from this side. No. Okay.
Wait. Okay, it did fit.
Came How did they fix it?
Well, the time's corrected.
Now it's okay, right?
We
You
corrected
what?
the time.
We corrected the time, Doctor. It was running.
Running?
Yeah.
I know the battery, but yeah, that's right. Initially, I want to change another clock. So hopefully, you didn't change battery, right?
No.
But we can, I don't know how it was.
How you fix it?
How do you know how they?
Yes.
Okay, they have somehow. I don't know how to fix it in there.
I bet it was barely even on there.
Yep. Okay.
No, that wasn't it.
No. Yeah.
You know what? There we go.
Okay. Okay.
Good enough.
Yeah.
Don't touch it. Now we have to hope it keeps real time, otherwise we
Yeah.
might be here
Yeah.
till 7 o'clock.
Yeah.
Hi. It is too cold.
Yeah. Oh no,
It's too cold.
my battery's.
That is low.
I've been trying to download this data set for 2 days. It's over 100 gigabytes. I finally got it downloaded, but because it's all zip files, I can't open it because there's not enough room on my computer. So I'm trying to get it moving over to hard drive. Because everything has to be difficult. Do you know how long it takes to download 100 gigabytes at like 30 kilobytes a second on,
Oh, I know.
university Wi-Fi?
I know.
I was like, oh god.
But not on university Wi-Fi, on my home Wi-Fi.
Like, well, I'm either this is going to download or I'm going to get a degree first. I'm not sure which at this point. That and watching my Mac try and push it all into the iCloud. I'm watching the iCloud just cry.
purge like last weekend.
Okay, just remind. Still, I think almost. All right. Let's try to briefly review what we discussed last time. We first considered the potential step. The potential step is that we have a potential. The potential suddenly jump at r is equal to 0, right? We have step. So we solve the solution and we discuss how about the reflection and transition. Classically, if energy is less than V naught, it always goes through with no reflection. But quantum mechanics, we discussed, found that there are partially reflection, and this reaction due to this wave behavior of the quantum state. Now, I think last time Theo asked a question. This is just plane wave, but usually it's be the wave packet, right? How about wave packet? I just answered that we know wave packet is some of all the K points. But each individual will have this behavior. So now I try to, let's go to consider the wave packet and see approximately this conclusion still holds true or not, right? So that is before discuss, continue with the energy barrier, so now let's consider this. Suppose the wave function is a wave packet, right? So that is sum of all the possible K. That is wave packet, right? So here we only consider one of K. But now if this particle move, we characterize the states of this particle move to be wave packet. Now for this case, can we get similar result, or at least we have this reflection does not equal to 0, right? So let's do this. This is a general, right? Then in our case, we have a region 1 and region 2, right? So the region 1, region 2 it is written in this way, right? The region 1, I'm going to from 0 to positive, that the positive K, that is the propagate, the incident, right? Just consider to the right, to the right. So this term, I just separate integral from minus to positive, is from 0 to positive K. So this is I, K is positive. Okay. Now I'm going to distinguish, since we have two K's, right? I'm going to use K1. And plus from minus infinite to 0, K1 exponential K1 x minus omega 1. Okay. Okay, that's right. That is for x negative. And for x positive, we only consider the particle from left, move from left to right. So that only this from 0 to the positive, right? We only consider this type of transition or propagation, right? So phi K2 E I K2 x minus omega 2 P K2. So for if we consider the packet. Okay, now we do the similar idea. So here you see I separated in two parts. So the region 1, we have two types of the wave. All the K positive, that is like incident to the from left to the right, and for the K negative is reflection, right? So now I define incident function, just a part of this. So that is from 0 to positive K1 y K1 x minus 1 t d then they reflect the function, that is, just take this minus infinite to 0, k1 x minus omega t dk1. But here, I can keep this as it is. But I want to make the same thing the integral, so I can rewrite this one. I think you agree. I just change this from minus infinite to 0. It's changed the integral from 0 to infinite. Now I'm changing to k by k1 prime. So here, if I define k1 prime is negative k1, right? So then this one, you can say this is a minus, but this is a function of k1 prime. So that's, and here is a minus I. I take the k1 prime. K1 is negative k1 prime, right? So I take negative, so here plus d k1 prime. Since I have a like sign here, so observe it here, right? That makes sense? So I write this, and then similarly translation is in the region 2, right? So this is all x negative, and then this one is from 0 to positive k2. K2x minus omega 2 t dk2. This is for x positive. So I separate this wave packet into 3 parts in different regions. Then the remaining part is now we are going to do this because this is a ratio of this current density, reflect current density to the incident, right? This is transition into current density to this. To calculate current density, we need d differential, right? d or I. Okay, we do this, so you have ik, but let me take I outside of k1, so inside, since this integral is for k1, I cannot take outside, right? So that's k1 and k1 exponential k1x minus 1 t dk1. And you take the complement conjugate, so I just do this, and the complement conjugate should be easy, right? So now, for reflect, sorry, this x. Reflect here, when I respect to the k1 prime, so that is negative I, 0 to the infinite k1 prime, sorry, k1 prime, exponential minus I, k1 prime, x plus omega 1 t k1 prime. And the derivative of this transmission term, similar thing. So I have I 0 to the infinite k2, right? Okay. Once we have those, we can calculate the current density. I just do one for instant, the remaining part for the reflection and the transition is same, so I just get final. Let's consider the first one. If we consider wave packet for the instant wave, current density formula is this, right? We just write down the general formula. This conjugate term and b sub n dx. Right, that is general formula. Then we just substitute this term, this one to here, and this one we take conjugate, right? So now I keep I h to n inside here. This integral, so I have over 2, right? 2 parts, because here, this one, I mean, this, oh, sorry, I have, I miss one of them. 2 parts, right? Yeah, I have a factor here. This also one of 2 parts. pi. So let's go to 2 pi. Okay, this one. So that is 2 pi. And the first, first integral from 0 to infinite is this one, right? Original. So k1 exponential I k1 x minus omega 1 t dk1. Then this one is from 0 to the infinite. Now I do the derivative, right? I have a ik, so I have a minus, right? So minus I k1. Just take this complete conjugate, right? Minus k1. K1 minus I k1 x minus omega 1 t dk1. So we have two integrals, and the minus the second term. Second one is from 0 to infinite. It's conjugate dk1, and then now here this one, right? Ik. So here ik1. Okay, that is all. Now we are going to write the next step. Here I have a minus ik or minus I, right? This is also minus I, so I take minus I outside. I squares minus, and the minus becomes plus. So here I immediately write down this, and the remaining part. Okay, inside I still keep this factor here. So this one, you see I omega 1 t, it does not depend on k1, right? And here, this is plus, this minus cancel. So there's no factor for the t. Then the only factor for k, right? dk1, and 0 to infinite, k1 minus I k1 x dk1. And then this term, since the negative sign will take out, so there's a plus. K1 minus I k1 x dk1. And we are to infinite. K1 I k1 x dk1. Okay. Up to here, we cannot do details since if we do not know this, it is not, they are not equal, right? You see, just this is a, if this is the term, this corresponds to complete conjugate, this one, and this is complete conjugate. So we just do analysis because this diffusion, if you remember, this diffusion is the formula from minus to infinite. E minus I, let's say k1 x. This is the coefficient when we have initial states of the particle, then project to, for getting k1, we have to do the integral. So this one is a kind of distribution. So I'm going to say this is a average k1, and I'm going to introduce, since I use average is too much, so let's use star. Sum of around, that means the most contribution is come from here, around the k1 star. What that means, this is a weighting factor for k1. Yes, it is become a sum of all the different, all the possible k1 points, but actually by distribution, what we know, it's always like this, like the kind of another wave packet in the k-space. So then we can approximate to represent this integral by just the function. So if this, then so we have approximately, I'm going to use approximate, not equal, right? Because they just try to grab the major contribution from the when k1 equal to k star. So then here I'm going to keep continue this constant. And inside this integral with a factor as approximately, I take this average around K1 star, or you take average, whatever you just consider this contribution with I K1 star x. So this function, this is an integrand, right? This one, since the dominance of that approximately equal to represent, let me just this, by substitute this K1 by this average K1. And similarly, for this one, so that is K1 star, K1 star, exponential minus K1 star x, that is this first term, right? Okay. Actually, the second term is the same, right? So you see here is this term, right? If you, okay, let me write down here. So that is second one. And exponential minus I K1 star x, and then K1 star and phi K1 star. Then you can see these two, this one multiply this one, actually is nothing but the absolute value of this, this one, the absolute value, right? And you see that only here, this cancel. This, I need another exponential term. So this one cancelled, right? Then there is approximately, I keep going. So you can see here that is h bar K1 star over, since I have a factor 2 the same, so factor 2 cancel, denominator n. And then do you agree? So that is dominant. Then this one you can consider in our previous case is like A, the coefficient. Correspond to that. So similar analysis we can have the others. So similarly, G reflect. Approximate. I just use approximating. All the others same. Just represent different wave function here, right? Here they replace the phi in with phi reflect. Now I'm going to give you is approximately equal to negative h bar over m K1 prime star and K1 prime star. So that is correspond to B squared. Then the transition is approximately equal to K2. K2 star. Okay. Which is correspond to C squared. I keep this formula, you will see they are similar. Okay, so now the R is J reflect to the J incident, right? J reflect here absolute value, so the h bar over m, and this h bar over m cancel, so we have K1 prime star, right? Prime star, and then the K1 star. And okay, of course now Okay. Now, in this case, since k1 prime and k1, they are the same, right? So we can cancel, and that ratio is only b squared to a squared. Here, we just take, actually we have to take this absolute value also, since this is absolute value, right? So absolute value here, if k minus be same k with k plus, right? So that in principle cancel, but at p here, then the t is J transmit and J incident. So that is K2 star over K1 star, and this is K2 star. And the remaining is we are going to find this, right? And this kind of a boundary condition. So from boundary conditions. Boundary condition, let me just quickly give you. This t equal to 0 and x equal to 0, because the boundary condition does not depend on time. So we just select that limit. Then we have this 1 over square root 2 pi from 0 to infinite k1, 5k1 dk1, since that exponential term all are 0, right? So that is 1. Then plus 0 to infinite k1, k1. That is the left hand side. Equal to the right hand side is equal to 1 over square root 2 pi, 0 to infinite 5k2 dk2. This is equation 1, and the derivative, so we have I 1 over square root 2 pi. Then we have a k1 dk1 minus I 4 pi. K1 prime dk1 prime equal to I square 2 pi k2. So we have these two equations, very similar with our previous one, only consider one limit, but here we have integral. And in this integral, again, we just take this approximately. If we take this one by represent this the peak here, so that like this constant cancel, right? So that is k1 star plus k1 prime star k2 star. Then this is I also cancelled, so we have a k1 star minus k1 prime star k1 prime star equal to k2 star k2 star. Just approximately represented by the dominant term. Then the remaining part do the same as we did before. So for example, I take a k2 star multiply 1 equation 1 and plus a minus equation 2 prime. So if I multiply this one, and then you can see this is the same. So I even separate, so this left hand side disappeared, right? Then the right hand side, we have these two. So we have this relation, and just give you immediately. So the sine k1 to K1. This is like B to A. This ratio is K1 minus K2 and K1 plus K2. And do the same thing, we have that's K1 prime star multiply 1 prime plus 2 prime. So in this case, we are going to, when we plus, these two cancel, right? So then it became this one with this one. That relation gives us K2 equal to K1 prime star plus K1 star and K1 prime star plus K2 star. If you compare with the B to A and the C to A in the textbook, instead of your star, if you just K1, K2, you will see the same. So with that, then we will have the reflection is simply is this one, is K1 prime star, let's use absolute value. Square K1 square 2 to this ratio and this one, right? So you see here. Okay, and here, right? This one. I think we have a square, right? I think I did I miss square? That is not serious. Either square or is not square. And this, so this ratio is this one. Take the ratio, and you will see K1 star minus K2 star square, and K1 prime star plus K2 star square. If you compare this one, you see, just replace this average K points, then these formula are similar. So transition K1, K2, star, K1, star. And the ratio here is this one is K1 prime, star plus K2, star, square, K1 prime star plus K2, star. Because we need absolute value, right? So this is just take absolute, since that take absolute value is better. And you can see here, E, I have a factor 2, I think that, yeah. If this, wait a minute, this is a K1. K1. So in the first case, we consider only one plane if these are same, so that's a factor 2. 2, then we have a factor 4 here. So if you not lost our discussion about this reflection or transition in quantum mechanics, so that's why to make this simple, we just consider only one K points, only one plane wave, and to. This, and for the others, we already discussed, right? So for this case, we discussed that so now energy here, then classically it will come to here and immediately at this position bounce back, right? But quantum mechanics, we have proved that the probability to find a particle is like this. Decay. So in this area, that's is really quantum mechanics say that still can find particle probability of particle above when the X is positive. So that means it can penetrate to the potential the step here for the in quantum mechanics. Classical does not exist. That is this case. That is all we discussed last class. Now today we keep continue to discuss another type of potential, the potential energy barrier, right? Potential barrier and wheel. So now let's consider the potential barrier. We just said the barrier is from 0 to 8. You have V naught. Then we discuss first energy lies in V naught, so that means you have energy here. And classically, that's be just sum of infinite when come particle here. This is like scattering, right? We have a target, and the particle come close to the target, we scatter to and go away. So this kind of this phenomena, but classically, it will keep going, no reflection, right? So now we are going to discuss in this case quantum mechanics. The reflection is not zero, right? And you will see very interesting. We have a resonance phenomenon. So now let's discuss this case. I think we already gave the formula region 1, 2, 3. So in this case, we have separated into 3 regions. So the Schrödinger equation also different regions. They call the potential. So now I will go back to the limit, right? Equal to E psi 1, which is x negative. So, okay, that is potential as a function of x. Then the region 2, we have barrier. Glass, right? We know. 2, and x in this region. Then 3, back to no potential barrier, like free particle. So potential energy is 0. Okay. Do the same thing as we discussed. I have a detailed discussion in the potential step. So now here, similarly, so I just gave the solution. Let's consider case 1. For this case, right? I'm already put it here. So the solution, the wave function also defined in 3 regions, right? The first region is phi 1, psi 1. Psi 1 here we have 2 possible, since we still consider the particle from the left-hand side go to the right-hand side. So at this boundary, it will partially reflect, right? So we have EK1 x, E minus IK1 x, and then some of the EK1 keep continue. So in this case, we have minus EIK2 x, and at this boundary we have reflection. That is also is this one come to here boundary. So that still need to consider, right? So here minus IK2 x. Then after here, go back to K1, right? Since here this Schrödinger equation is they are the same, only the region different. So the solution here in first one, we have an incident A, I'm going to say A exponential I K1x plus reflection, B is E minus I K1x, and in the region 2, set 2. That is a C will still keep going, exponential I k2x, because the energy here is different, right? And plus D exponential minus I k2x. Then the region 3, we have a set 3x. That is only considered keep continuum. The reflection is not the reaction or response for this incident. So that is I'm going to use E I k1x. Since in this case the k is the same, so here we have a k1 2m e over h bar, k2 is 2m e minus v naught. Okay. Now next, let's try to find the coefficient, the A, B, C, D, E from the boundary condition. Find the relation between those coefficients, since we are going to discuss reflection and transmission. So let's first boundary condition. How many boundary conditions? We have 2 boundaries, right? X equal to 0 and x equal to a. Each one have a function itself and first order derivative. So totally we have 4 equations. Okay, so here, first one is psi 1, 0, when x equal to 0 is equal to psi 2x equal to 0, right? That is first boundary here. Second boundary here. So that boundary is psi 2, a, right? X equal to a, not 0. And psi 3, a, right? So now I'm going to say, all right, 1, 2. Then another 2 equations from the derivative. So derivative is d psi 1 x dx when x equal to 0 is equal to d psi 2x dx when x equal to 0. This equation 3. Equation 4 is derivative of psi 2 and x equal to a equal to d psi 3 dx and x equal to a. That is, so we have these 4 equations. Then substitute this formula here. These 4 equations is come to this relation: a plus b equal to c plus d. I'm going to say 1 prime. 2 prime is a c e I k 2a plus d e minus I k 2a equal to e exponential I k1a. Is 2 prime, right, from here. So be careful. Second boundary is x is not equal to 0, it's equal to a. Then this equation 3 and 4, it will reduce to 3 prime and 4 prime. So now I'm giving you I k1 a minus b equal to I k2 c minus d. 3 prime I k2 c e I k2a minus d e minus I k2a equal to I k1 e I k1a. That is 4 prime. Okay, so I'm going to use I k2 multiply 2 prime and then plus 4 prime. So here I multiplied k2. So you have multiply k2. Here we have a k2, right? So these 2, if I add together, so this second term cancel. We are going to find plus. Okay, plus. So we can find c. C relation is e, right? So now let me just give you the final result. C is equal to k1 plus k2 over 2k2 and e exponential I K1 minus K2. A. And give this equation is 5. Since I use prime, let's say 5 prime. That is a relation between C and E. Now I'm going to find a relation between D and E. So what we need to do, just minus, right? K2 multiplied 2 prime minus 4 prime. So then we can have D is equal to K2 minus K1. 2K2 E exponential I K1 plus K2. That is 6 prime. The third one, now we are going to find the, our goal is find the transition, right? In this case, how much transition must behave like, right? So transition is ratio between A incident and E after transition, after the region 3, right? So that is our goal. Now we are going to find A, relation between A and E. Then which one we are going to use? We can use K1, IK1 multiply 1 prime and plus 3 prime. So this gives us the relation is 2I K1A equal to I K1 plus K2 C plus I K I K1 minus K2 D. 7 prime. This, I give you the details. When you deal with this, you should be careful step by step. If you miss some of sign or some of by typing one became K1 became K2, then your result became is wrong, right? So just go to some detailed steps, let you know how to do that. Then later I'm going to skip that step. Substitute 5 prime, since we know D, C, D, right? To this one. Since we are going to replace C and D, then we are going to find A with E. That is our goal, right? 5 prime secant 2, 7 prime. So 2, just 2, right? 2. So then give us finally, and just give the relation between A and E. We have A equal to E exponential I K1A over 4 K1 K2. And inside is 4 K1 K2 cosine K2A minus 2I K1 squared plus K2 squared sine K2A. Little bit complicated. Oh, I think I have. Oh, yes. Okay. Now, this is what we want to see. Transmission, right? Transmission is the transmit current density to the incident current. This formula is, that is the same as we did before, so I think this one how to get this one, as you know the wave function here, right? And calculate each current density. So I just skip because this is same as the potential stack, similar stack. So because functions are similar, then you can get similar way, right? So just direct. Now we have this ratio E to A, right? So ratio E to A, and just take inverse and take square. So and this one cancel, right? Okay, and that is, let me just give you final. 1 over, not final, but at least this that I already organized this as K1 square minus K2 square over K1 square K2 square sine, I think it's B square, I made a mistake. It's B square. Yeah. Okay, up to here. Now, this formula you can see we have this term. This term make the kind of oscillation, right? So the probability of a transition, it will depend on the K2, how much it is oscillating, right? So we are going to discuss. Before discuss, okay, that's it. So now we are going to substitute K1, K2 in terms of energy, since that's defined as the unit, right? So let's first consider this K1 square minus K2 square, K1, K2, right? This is this one square, so if I take this one, I just give final result since you know K1, K2, right? V naught square root, energy minus. So then this K1 square minus K2 square over K1 square, K2 square is take this square, right? V naught square. Okay. Then that is, here we have also Ka, right? We consider this coefficient, this constant is this, and now how about this one? So now first things, K2A, K2 is 2m E minus V naught. Over H, that's K2 and A, right? So now we take 2m V naught A and H bar outside. So we have this, okay, 2m V naught over H bar A. If I take this V naught, then this there's a ratio, right? That is energy V naught minus 1. So I'm going to introduce lambda is A over 2m V naught. And epsilon is just a ratio. So epsilon, since in this case energy is higher than the energy barrier, so this must be always larger than 1, only when energy equal to V naught is 1, right? So that is epsilon, the region or a large value. Now when we introduce this, so we can rewrite this one in terms of the lambda and epsilon. So T, rewrite T is 1 over 1 plus 1 over 4 epsilon minus 1 sine square lambda epsilon minus 1. That's now we can discuss in terms of epsilon and lambda. Now it is slow,
Yeah.
almost. So we cannot rely that.
Oh, wow, yeah, that's really
Yeah.
slow.
This is it, because I think now
Oh,
maybe
it got
battery.
stuck with the
Yeah,
second
we
hand
need
not
a-
going anywhere.
It's
we
going
change
backwards.
battery if it works, and then okay.
Yeah.
All right, so now let's discuss this. Discuss.
A nice effort, friends.
Since the information from here that's interesting. First, what is we didn't discuss or calculate this reflection, right? The coefficient. So, but we always have this. So very easy. If we know this transition or transmission coefficient, refraction coefficient just 1 minus, then we just manipulate this, so I give you the result, which is 1 over 1 plus 4 epsilon minus 1 divided by sine square lambda square root epsilon minus 1. Okay. Do we have a reflection? The answer is yes, right? Since if epsilon is not equal to 0, not equal to 1, if equal to 1, this is 0, but if equal to 1, there's also this term. So whatever, at least here, you can see for given energy, if energy larger than V naught, it can always has a partially reflect. that is totally different with classical. Okay, second one is we are focused on the transition. That's interesting. So if energy is much higher than the energy barrier, so that means epsilon is much less than 1, right? Larger than 1. Then we come to here. So this term is whatever is a some finite number between 1, because this is a sign, right? But then you look here. So if epsilon is larger than 1, so the denominator became bigger, so this term becomes small and small. Then denominator 1 plus a small number is approximately what? What that means? It means if the energy is much higher or higher than the potential barrier, it is easy, almost no reflection or effect by this energy barrier. The particle feel like a free particle just goes through. So that is this case, when energy very high. Well, there are some interesting here. Look at this term. Is this term equal to 0? So this is again also 1. But this 0 does not mean it's this condition. It is some particular condition. So if lambda equal to 0, that means lambda epsilon square root is equal to n pi. N can start 0, 1, and 0 is, let's just consider 1. If 0 is no any contribution from here, that is correspond to E equal to V naught. I just, let's keep this one in mind, 0. 0 means energy equal to the potential energy barrier, just here, right? So that is, we are going to discuss next one. So let's consider this case. Then if this condition, that means lambda satisfied, so that we have energy, epsilon, has a spatial number, right? Depend on n. So if you take the square root and move this to the left-hand side, so you can see we have epsilon n is n pi over lambda square plus 1. Then that gives us energy. It's also dependent on n. Since En, you see the epsilon is the ratio, right? Ratio energy to the V naught. If this ratio has special numbers, then that energy will correspond to that special number, because in that case, this is equal to 0. So let us V naught, let me tell you this one. That's V naught plus this n square pi square over, okay, then just first minus lambda, then we substitute lambda. So here, V naught n pi over lambda square, right? It's just this one. And then we are going to substitute lambda. So lambda is here. Then you will see here, it is V naught. Lambda will have a denominator, right? So V naught cancel this one. Plus h bar square n square pi square over 2ma square. You have the quantum in the senior, the undergraduate level, right? You're familiar with this energy, right? This is infinite potential well, right? We have this allowed energy spectrum is discrete. So you can see here, what happens when we have this? The transition coefficient is 1. So if that case, T equal to 1, because this term is 0, right? So 1 plus 0 is 1. Then what does it look like? This one does not mean its energy is much higher than the potential barrier, but it just gives some certain number above that. So we'll have in the transmission as a function of epsilon. Then we have epsilon 1, epsilon 2, depending on n equal to 1, 2, right? Epsilon 3 higher. So then if this is a 1, if this is 1, So we have one here, one here, one here, right? And so then this, let me first from 0. Let me write down here, and then I give you discuss this. Okay. This, be careful, this curve is not this transmission included only this energy higher than the potential well. If this is a 1, that is correspond to energy equal to this one. And this region is energy, this one. So this region is so we are talking about from epsilon larger than 1 for this case, right? So what you can see is we have a certain transition, but with certain particular energy here, follow that formula, the transmission is 1. That is 100% transmit, no reflection. So we call those are the resonance. And this resonance means, so here is energy barrier right here now. So we have energy, some of particular energy, E1, E2, E3. For such particular energy, you have the system will 100% transmit. Otherwise, you have only part of the transmit, part of reflect. So this phenomenon cannot be explained by classical mechanics, right? It's totally the quantum mechanics behavior of this. Okay, then the number 4 is epsilon equal to 1. That is close to 1 or so. In this case, this again is almost 0, right? But you know, let's see. Okay, in this case, this one we are going to use approximate the sine theta approximately equal to theta. We are going to use that. Lambda. So here, sine square, let's take this square. Then we have this t is approximately equal to 1 over 1 plus lambda square over 4 epsilon, which is a constant. That is the constant. It's finite. And similarly, r is 1 minus t, right? Is also constant in this case. And that means also has a reflection. Okay, this for this interesting phenomenon that we can see we have energy barrier. What happens when the particle goes through? Quantum mechanically is means that it depends on the energy. It may partially go through transmit, but maybe 100% if the energy satisfies this. And that is due to this here the constructive. Here the wave, this inside the wave also constructed, make the same magnitude here. So you have this transmission. Now, similar discussion, we can have all the similar results for the case of a potential wave. So the only difference is the sign for the V naught. So now let's just give it the result. For V naught is negative, that is real, but still have, because energy positive, right? Still have this result. So for this case, solution, everything the same. So only here we have K1 still the same as what we discussed. But K2 is just opposite. It's 2m V naught, that's not opposite, plus. Previous E minus V naught, right? But V naught is negative, so this is plus. Now I'm going to use absolute value over H. So this is the only difference. And the others are all the same, so we can give you all the results, do this boundary condition. Now let me give you the result for transmission. But let's say I use W means the potential wheel. The transmission for potential wheel, the formula is again here, same. So that is 1 plus 1 over 4 epsilon, is minus 1. Or plus 1. Okay, now I mean this is a different sign. Square lambda square epsilon plus 1 here. The epsilon, the lambda is same, but we take the absolute value. 2m, now absolute value V naught. Let me see, lambda over h bar 8. And epsilon is E over the absolute value of. So that's different, because here, this is a plus, right? So we have this plus. But only here, the difference from this one, here, this is a minus, this is a plus. So this is a plus, this is a plus. If this plus, we will not worry about epsilon go to 1, right? Since the denominator will not go to the infinite. So this discussion is a little bit simple, but still we have a sense of if this equal to 0, right? This one, we will not worry about here. So this one is epsilon the value. The energy is equal to 0 to 0, right? So that is in this range. That is here, from 0 to 1. So the textbook didn't mention, they gave the figure for this transition, but actually it depends in which area. In this region is region 1 is negative. This one is, okay, let's see this one. V naught positive and E naught negative. This one is V naught negative. And E, of course, in this case, it will be positive, that is definitely slightly. So that is in two regions here. That is for potential well, this area, potential well to transmission, this is a potential barrier. So then the same thing. Since in this case, okay, so in this case, if that's a discussion. If this one sine lambda epsilon plus 1 equal to 0, so we have epsilon, same thing, we have epsilon n is n plus n pi over lambda squared minus 1. And the energy is n square h bar square pi square over 2n a square minus a naught. Is this case. And in this case, again, we have a sinusoidal since we have this term. So when this term equal to 0, we still get 1. Then I think, wait a minute. I still, wait a minute, over here. So that is 1 here. And then, I think that is correct. Epsilon 1, epsilon 2. But this all smaller than 1, so that is this case. Let me see this one. This one, I think that is what I said. This one still, ignore this when the action is smaller than 1. I think that's is this case. Since this case is tunnel effect, this has some finite numbers, which we are going to discuss. This case, tunneling effect. But the ratio It's always smaller than 1, yes. So that is that case. Okay, I discussed here, right? So that in this case, that's 1, then that gave a T equal to 1. This again is a resonance effect. Then when energy, since always positive, so if energy go to 0, this go to 0. If this go to 0, here, this go to 0, it will not affect this one since it's still finite, right? This is a still cannot give any 0 case, so that is not significant. The only this case is interesting. Okay, now we consider if the energy is lower than the potential energy barrier. Okay, here. So now we have in here. Look this case. This case we know if a classical particle come down to this bed, the boundary here and you're totally 100% respect or bounce back with light. No transmission to this area of sleep. Now let's look at the quantum mechanics. And quantum mechanics give us the probability to transmit this energy barrier even though the energy is lower than the energy barrier. So in this case, this solution, let me give the solution here. Since in this area, energy is smaller than the V negative, right? Similar as we do this energy step. So this should be V naught minus E. Then this K is real, not there's a solution is different. Region 1, psi 1x is again the incident with wave and reflection. Here, in this part. Okay, now I'm going to write. So in this part, let's first take this one. K1 x plus b minus I K1 x for x negative. The second region, psi 2. Now here, since this energy is lower than V naught, so we have a real solution exponential K2 x plus d exponential minus K2 x. This is a different. Since here you notice that we have a negative sign, so the solution is not sinusoidal from the exponential, right? Either decay or increase. But here we cannot drop this one, right? Finite, right? Not go to infinity, so we don't worry. So this one is the key. Then the third one is now again we just take the go further to the right, so the E exponential go back to K1, right? Okay, so that is the solution, and let me give you K1 in this case again. 2m E4H bar, and K2 is 2m V naught minus E H bar. Now let's discuss. First, give this coefficient, then we can discuss the reflection and transmission, since we need that. Okay, boundary condition. Again, we have 4 boundary conditions since we have 2 boundary and 4 equations. So there's 4 equations: A plus B equal to C plus D. This is equation 1. And K1, A minus B, this is derivative of this at x equal to 0 equal to K2, C minus D, that's equal to 2. Then the derivative is this is a derivative for this, and then for the dominant of A, we have a C E K2A plus D E minus K2A equal to E exponential I K1A, equation 3. And equation 4 is K2 C E K2A minus E K2A equal to I K1 E I K1A. Four equations and do the similar step. So, okay, the intermediate step is C. How to do that as I did as before, so I just give you the result. C is a function of E, 1 plus I K1 over K2 exponential I K, sorry, K2 has no I, so now this is exponential I K1 minus K2, 8. And the D is half E, 1 minus I K1 over K2 exponential I K1 plus K2. So B over A. B over A is respect to the reflection, right? So I give you this. Space is not enough, then come to here. B over A is minus I K1 squared plus K2 squared over K1 K2. Hyperbolic sign here. Since we have this not I, so that one we have hyperbolic. Inside 2 cosine hyperbolic K2A plus I K1 squared minus K2 squared over K1 K2. Hyperbolic sign K2A over, basically in the denominator. And E over A, which is correspond to the transition coefficient, is equal to factor 2 exponential minus I K1A. Inside 2 hyperbolic cosine K2A plus I K2 squared minus K1 squared K1 K2 hyperbolic sign K2A. Okay, with this now we finally can have this coefficient of transmission and reflection. This reflection is B squared over A squared. Then we just take that square, so we have this take this as K1 squared plus K2 squared over K1 K2 squared. Hyperbolic sine squared K2A. And 4 hyperbolic cosine squared plus K2 squared minus K1 squared over K1 K2 squared. Since here we have I, right? You have, when you take the square, you need take this real part and the imaginary part. So that is finally we have all the real part. Okay, so hyperbolic sine square K2A. the transmission is E squared over A squared. That is 4 times hyperbolic cosine square K2A plus K2 square minus K1 square over K. Over K1, K2 square. Hyperbolic sine square K2A. So definitely it's not equal to 0. I think yeah. Let's say that if that is not 0, that means it has the possibility to transmit even though we have a high energy barrier, high energy lower than that, we still can have this transmission and we call it Carnot effect. So let me keep this one, finish this next Monday. Discuss the physics here. Then we go to the, those are all continuous spectrum, right? Then we are going to discuss this. This grid spectrum is the bounded states. So for the unbounded states, we are interested in how about this transmission and reflection. So that is the focus in this case. And how to determine that, we need to know, separate each part, and then we are going to use boundary condition, then calculate the current density, and can determine the relationship, right? The boundary condition sometimes is complicated. We need to be careful when we deal with those equations. Otherwise, it is same scale procedure, so that is easier. Just do it carefully. Okay, we still have time. The homework to next Wednesday, right? So I think except this 4.2. But I think that you're also familiar, you have that experience to solve this infinite potential well. Otherwise, the first 3 problems you can do yourself. Okay, if you have any question, let me know.
You're in the quantum realm.
I was in the quantum realm. Absolutely.
Oh, that was a superposition. I just vanished.
You were here and not.
Yeah.
Now I see. What is your momentum?
Looks like a lot of potential.
Much potential.
I'm a free particle.
Maybe Sri Lanka.
Huh.
Sri Lanka.
Oh yeah,
Okay,
those are good.
I think Taylor and Perry, you have your talk. Change the batteries.
I don't think it's a battery issue.
You think the battery?
No, I don't think so. Look, it's still ticking.
Sometimes that happens.
Well, we'll
Oh,
try it.
still take it, so,
No, like when power is not enough, sometimes that.
Oh, it might not be able to get over
well,
the
I know that I changed that one last year, but
Oh.
then they stopped very quickly. So now, so let's see if it works. We only need one, right?
Yeah.
Okay.
Oh, it's just back and forth.
Get in there. There we go.
5, 20.
5, yeah, almost 17 or 18.
Error on the side of 18.
Yeah, 17 earlier, better than.
All right.
All right, let's see you tomorrow. Thank you. Thank you. I keep this battery here, so next time.
Just in case.
extra jacket in my car. Winter coat. Winter jacket? Yeah, do you need one?
When I moved,